Okay, so the next problem we're going to be working on is different looking cross section here. So you've got the geometric properties of this cross section, and we want to find also the prime axis and the corresponding prime moments of inertia for that one. So first things first, find the centroid. So basically, if we're going to be measuring from the bottom left, then basically what we can do is we can break the components up in the following bits. So I'm just going to choose this cube, this long thing here, this squat one here, and then this other shorter piece here. So x bar, again, is going to be equal to the sum of the x bar components for the individual ones times the area of the individual ones all over the total area. So for A here, the x bar is located, let's look at 5 millimeters from this right corner here. Area, again, that's just going to be 10 millimeters times 70 millimeters. This next one here, it's got its centroid. It's located here at 20 millimeters. And its area, 30 millimeters times 20 millimeters. This next one here, it's got its centroid here, located here at 50 millimeters, and then 10 times 70 millimeters, and then all over that total. So that ends up giving us an x bar that is located at 20.9 millimeters. So kind of right about there. And we're going to be using some tricks for this one in order to avoid having to recalculate the same thing we just calculated. So we know that this object here, we know that it is symmetrical about an axis defined by x equals y. So we know that the y bar is also 20.9 millimeters. So now that we found that, basically I'm going to redefine our coordinate system so that, I trailed off in the middle of writing that sentence, didn't I? Well, this is what happens when I do problems in the middle of the bloody night. In order to place our axis origins at the centroid. There we go. So we will be calculating our I-X's and I-Y's based upon rotation of the rotation about those axes passing through the centroid. Otherwise, we'll be getting the wrong values due to the parallel axis theorem kicking in. So, next up, let's start at it. So, let's start with Ix. So we got Ix can be found just looking at the combination of the contribution from A, contribution from B, and the contribution to C. And each of those ones can be found by their individual inherent Ix's, the Ix prime A for A, times the area of that component and the distance between the centroid of that component and the centroid of the new of the overall structure squared. So again, it will be, these are all rectangles, so we know that the IXA prime is, that's just B, that's a terrible looking B, BH cubed over 12. And of course area is just base times height. So for that one, shouldn't be too difficult. Our BH cubed over 12 plus the area times our dy squared. So dy squared in this instance is 14.1 because the centroid is located. Centroid for that thing is located here at 35 millimeters minus our 20.9 millimeters gives us 14.1, which gives us a value here. The IX IXB here, similar idea. We're got the base 20 millimeters, got the height 30 millimeters cubed, divided by 12 area, and then we've got our our dy squared. So in this instance, the centroid there is located at 15 millimeters, kind of from here. So from here to here is from the centroid to that point is going to be 5.9 millimeters, which works out to 65.9 times 10 to the 3 millimeters to the fourth. And next, similar idea for a C. So smaller height, longer base, divided by 12, area, and then our distance from here to here. This from here to here is 5 centimeters. So 5 millimeters. So 20.9 minus 5 gives us our 15.9 millimeters. So all that 101.5 times 10 to the 3 millimeters to the fourth. All that adds together to give us our 595.4 times 10 to the 3 millimeters to the fourth. So, yeah, we could redo our calculations, but again, this thing is symmetrical about the xy axis, x equals y axis, so we would get the same value when we punch y in and vice versa. So that lets us solve for that, which gives us our j as well. So j is always, the j is ix plus iy. So now we got 1.19 times 10 to the 6 millimeters to the fourth. Unlike the previous examples that we've seen, our product of inertia isn't going to be 0, because for this particular thing, neither the x or the y axis is a plane of symmetry. There is a plane of symmetry, but it's not about that axis. So we need to find out what our product of inertia is. So parallel axis theorem comes into play here. We're basically summing up the individual components of the product of inertia and for those individual components, and the a times dx times dy. So that ends up, these end up being relatively simple because those are all rectangles. So we know that those rectangles, they do have an axis of symmetry about both the x and the y axis. So we know that the IX y prime for all of those is going to be 0. I could let you do the calculations, but why bother? If we identify that an x that's the case, just state it. So yeah, because those are symmetrical about the x-axis or about the y-axis, the individual components are 0. So the only thing that causes there to be a non-zero ix overall is the combined sum of these area dx dy terms. So again, just kind of measuring from our centroid here, going to our displacement from the centroid to the individual to the centroids of the component parts gives us this, and we'll just basically take those values, that times the area for A, that times the area for B, that times that times the area for C. I'll add that all up, and that'll give you your I, X, Y, which in this instance works out to be negative 339 times 10 to the 3 millimeters to the 4th. So we got that. What do we do with it? Well, okay, so we want to find our prime axis. In this instance, again, we use this relationship here to find how much we need to rotate to get to our prime axis. However, our Ix minus Iy here, that's 0. Those two things are equal, so this is 0. So basically, we have this value here is an undefined, approaching infinity because we're dividing by 0. So that's okay. That happens with tan. We know that happens with tan. So we know that happens with tan at 90 degrees and 270 degrees. So if that's undefined, so basically, if that happens to tan at 90 degrees and 270 degrees, that means that the prime axes are going to be occurring at half those values. So we need to rotate this. We need to rotate our frame of reference 45 degrees, or we need to rotate our frame of reference 130 degrees in order to get our prime axes. And that's probably basically kind of what we expected it to look like, right? That means that we are rotating it such that one of our axes, either the x or the y, is going to be an axis. Is going to be one of the axes of symmetry. Or the axis of symmetry, because we've only got one axis of symmetry for this particular shape. So now that we know kind of how much we're going to be rotating, we can find out what effect that has on our Ix and our Iy. So we got this formula here that we use to calculate that. It's from our textbook. And we simplified it a little bit. Ix plus Iy over 2 is just equal to Ix when Ix is equal to Iy. Got this term here that zeroes out. So we're not worried about this, which means that the cosine to theta goes away here. Which means that we are left with Ix, it's supposed to be an x. Ix is equal to ix prime is equal to ix plus ixy sine 2 2 theta. So again, for a 45-degree rotation, sine of 2 theta is 1. 2 theta is 90 degrees. Sine of whatchamacallit, the sine of 90 degrees is 1. So that gives us our ix prime with the 45-degree rotation as the ix that we had originally found. Oh, just 1 second here. When I said that this was supposed to be y, that was me being wrong. Sorry, this was supposed to be an x, that was me being wrong, because I didn't notice didn't realize the sign here. So ix prime is equal for this situation is equal to ix minus the minus ixy sine blah blah blah. The iy prime is equal to iy plus the ixy sine 2 theta. So yeah, sorry, I thought I made a mistake and made a mistake in thinking I made a mistake. So anyways, back to where we were. Alright, yeah, so our x prime is going to be, for that situation, just the what we had initially minus the ixy, which in this instance is a negative value. So ix is going to increase when we rotate our frame of reference to here, which gives us a value of 934.4 times 10 to the 3 millimeters cubed. Sorry, not cubed, to the 4th. Similarly, our I prime y is equal to our I y that we initially calculated, plus the ixy term, which again is negative, so our iy decreases to 256.4 times 10 to the 3 millimeters to the 4th. So that's the that's the values that we get for this shape here. So we got we are maximizing our ix when we're orientating it like this, whereas in this orientation we are maximizing our iy. So yeah, these are the values for here for this orientation. Again, because it's for this orientation, you just switch the two values. Our iy, our iy in this situation would be the 934 times 10 to the times 10 to the 3 millimeters to the 4th. So that gives us our values at our prime axes. Yay! Hey, we're done.